Got it.
Good morning, everyone. Welcome to C&E Sales Monthly Webinar Series. I'm Jeff Butler, the Technical Manager here at C&E. Today's webinar is titled Programming and Configuration Guidelines for Siemens Safety Advanced. Our presenter today is Steve Wright, Safety Specialist with C&E. Steve holds a BSEE from Wright State. He's a registered PE. He's a certified safety specialist and a TUV functional safety engineer. Steve's been with us since 2008. Just a few housekeeping items before we start. If you have questions during the webinar, and we hope you do, please submit them using the control panel tool on the right side of your screen, and we'll address them at the end of the session. If you don't see that tool, click on the red horizontal arrow. Everyone registered for this webinar will receive a link to the recording, so you can go back and review it later if you'd like to, or share it with someone else. Please be sure to, Please be sure to attend next month's webinar, hosted by Jeff Weaver, Automation Specialist at C&E. Jeff's topic will be Siemens S7 1500, TIA Portal, and Profinet implementation. This webinar will be hosted on May 11th at 10:30. I'll now turn today's webinar over to Steve.
Good morning, everybody. Thanks for taking a few minutes to see this. What you should see on your screen right now is just a couple of the topics we're going to talk about today. Just a couple of them. We'll go over some general guidelines for configuring a safety project with the S7 1200 and 1500 products, and then we'll look at some of the safety functions that are available for the 1200. These are also available for the 1500, but we'll look at them in a little more detail. Here we go. So generally, when you consider implementing safety in your PLC program, there's a couple of things you should consider. What you want to do is you want to distinguish between the safety and the non-safety functionalities of your program. In simplest terms, we do that in a Siemens PLC by running a separate safety program. But you want to keep those things separate because they really are. Generally, you could describe the safety functions as sort of a shell that surrounds your process functions that doesn't let anything happen unless the safety is satisfied. But this is important consideration to optimize the construction of your project. And we want to use appropriate languages. This is not a huge point of contention in a Siemens F program because there's only two languages to choose from. Ladder diagrams, which probably most of you are most familiar with, or function block diagrams that can give you a little more concise picture of your logic. We're going to talk about these more later in the presentation, but you want to use the validated software function blocks that are provided by Siemens as much as possible. The important thing to remember, and you keep this in mind when we look at some of the details of some of the blocks, is that these are tools and subfunctions that you can link together in your own safety program. The thing to remember is that linking them together inside the safety program is in itself still a safe function. It's really the access, the in and out that you have to be more concerned about. But as long as if you can string them together in a way that satisfies the compilation of the program, they will execute as they should. And then finally, you want to develop and use some guidelines that make sense to you. And in that note, we'll look at some of them really. I'm sure that some of you have been involved in projects with customers or even your own organization that have very detailed, very specific instructions for building a safety program or even any sort of program. My job here is not to lay you a big one on you, but just there are some general considerations that you should keep in mind. You want to be able to read it. We've all been through that, trying to decipher somebody else's code. In a larger projects and in a faster moving programming environment, you want to set up rules and standards that are consistent and so that other people could use them, so that then the guy sitting next to you could pick up your project and continue with it without having too big a learning curve. Shown toward the bottom of the screen are a couple of references where you might get more detailed instructions on programming guidelines. That first one is a link to some Siemens documents. If you can search for that document number on the Siemens support site, or even just Google Siemens and that support and that number, and you'll get a link to some pretty extensive programming and style guidelines. Second one is a link to the PLC Open website that has much more extensive coding guidelines that may be of use to you. Just one thing I'll speak of a little more detailed is the naming conventions you use for your objects in your program. Some of the examples I see here, show here, are actually taken from existing computer programming languages. The camel case, you can Google that and you find all the specifications for it, but generally it starts just like I show here, that you don't use hyphens or underscores. Personally, I find this is something that slows down my typing a little bit. So, and then Pascal case is very similar to camel case, except that it just starts a little differently with a capitalized letter. It's not my intent here to shove one of these standards down your throat. Even in my own programs, I tend to stick mostly with Pascal case, but I'm not opposed to making changes if it reads a little more easily to me. On the PLC Open site, their naming standard is what's called a Hungarian notation, which is much more detailed and actually describes the type and some other details about the names you use. Like you see here, the X in Hungarian notation designates a Boolean instance, and the S represents that it's a safety function. There's, you can get into longer names if you want to, but really the idea is that this is going to be readable. You're going to name things the same way all the time, and somebody else can pick it up and understand what you're trying to say. Because we keep our safety program separate as much as possible from our standard program, it's going to be required to communicate between those two programs. And this is just a chart showing some of the details of how Siemens F processors communicate between the standard program and the Failsafe program. In general terms, we want to use data blocks rather than merely bit memory to communicate between them, because I can organize the data blocks in a little more clear fashion. There are a couple of restrictions though, as you see in the chart. The elements of a data block, a standard data block, as you might suspect, can be both read and written in the standard program, but in the safety program, only one of those can either be read or written, but not both. Similarly, if I create a failsafe data block in the safety program, I can both read and write it, but in the standard program, I can only read it. Bit memory behaves much like a tag from a standard data block, in that in the standard program, I can read and write it all day, but I can only do one of those in the safety program, either read it or write it. One of the changes that came about with the introduction of the S7 1200 and the S7 1500 processors in the TIA portal was changing from using what's called a value status bit versus what had been used in the past, and with the 300 and 400 processors a QBAD bit. QBAD designates a module or a channel error. So it's true when the channel or the module is faulted or it requires an acknowledgement, as opposed to the value status reported by 1200Fs and 1500Fs, in that when the module or the channel is in the run state, the value status is true. So it's the opposite state from the QBAD, and we'll see this when we look at some of the connections of some of the software blocks, that they still retain the name QBAD, but we have to internally, and we have to supply the value status in the correct manner. If we start to look at some of the safety blocks that are provided by Siemens, if you're using any of them, probably the most commonly used one is the e-stop block. This block does two things. It defines the acknowledgement method for the output. In this case, it can either require a manual acknowledgement or an automatic acknowledgement. And it supplies a instantaneous off output out the Q terminal, or a time delayed off in the case of a stop function, a category 1 stop, out the Q delay output. Down at the bottom of the screen, I just show a way that I sometimes use these blocks. If I have a selector switch that requires I require a failsafe selection in my program. What you're looking at there is it would be a 2-position or a 3-position selector switch that has 2 normally closed contacts on each side. Either of those pairs of normally closed contacts are driven open by the action of the switch, and the connection to the PLC is actually the opposite state. So when I turn the switch to the forward position, I'm going to drive open those normally closed reverse direction contacts and allow the forward direction contacts to close. So it gives me a 2-channel positive action on an input, much like hitting an e-stop. The next function that's used probably the most is the feedback block. You see the sketch on the left-hand side of the screen just shows a fail-safe output, and it's normally closed feedback contact connected to a standard input module. This is perfectly acceptable. It's up to you to decide whether you want to hook that contact to a standard input module, or it's also acceptable to hook it to a fail-safe input module. But what this block does is, the Q output will turn on when the on input comes on, as long as the feedback input is in the correct state within the feedback time, shown here at the bottom here within this 100 milliseconds. And what this block is checking continuously while it's in operation is the opposite state between the Q output and the feedback input. So if it sees a discrepancy or sees the same state between those two, it's going to turn on the error output, and the acknowledgement for this block is really acknowledging the error in the feedback signal. So this feedback block, as long as the contactor and the contacts are working correctly, will come on and off just with the on input cycling. But should it get an error, and it will need an acknowledgement to clear that error. It won't turn the Q on with a 1 at the error output. Down at the bottom of the screen, there's another link to another Siemens functional example where you can see these in a little more detail if you choose to learn about those a little more. Safety doors, I've spoken of this a couple times before in some of the seminars, but safety doors are a little bit different than e-stops. First, if we look at the bottom of the page, the term probably everybody is familiar with is force guided. Actually, the correct term to be used now is positively driven contacts. And what that means is that in a device that has both normally open and normally closed contacts, the switch or the relay is constructed in such a way that those two types of contacts can never be closed at the same time. That's what it means. It keeps a certain minimum gap in there should it fault. The other important consideration in door applications is to use them in a positive mode of operation, which means that the switches that are monitoring the door are actually switched by a rigid connection to something, either the door or the arm that they sense us with. For instance, a whisker switch is not a positive mode of operation. In the picture above, if we look at how that door is being monitored, the two switches are actually one switch with a normally open contact that is actuated. That's the switch that's closest to the wall on the left, whereas the other switch is a normally closed contact that is unactuated in the closed position. And you see that the positive mode of operation is that as soon as that door moves open, the normally open switch is allowed to close or allowed to open, and the normally closed switch is positively driven open. So that's the way it monitors the action of the door in a way that protects against any sort of mechanical maladjustment or out of alignment or distortion of the door action in the switch position. So there is a function block, the SF door block shown here within the safety functions that could be useful if you want to guard a door in that way. So how it works is much like we discussed before, is in the open position, the door would be monitored by two single channel door switches, one of which is actuated in the open position, the other one's actuated in the closed position. Rather than using one out of two dual channel inputs, it can use any two 1 out of 1 inputs. They may not even be on the same card. Probably the other feature in the connection that you might keep in mind with using it like this is you probably want these internally sourced just to get a little protection of the actual wiring to the switch. But what the function block does is that as soon as either one of the IN terminals goes low, the Q goes low. And it has to, before the Q can go high again, it has to see both of the inputs go low. So you see, this is the first instance where the function block has Q bad inputs, where in a 1200 or 1500, we're actually going to supply it the negated state of the value status of those, in this case, of those two input devices. What it's doing here in the function block is should the module that's connected to the inputs fault, you don't have to reset this particular function block. Down at the bottom, you see that we can configure whether we have to open this at machine startup. That's what the open_NEC input does. So, once the PLC comes back to life, I may have to open all the doors. And then the acknowledgement in this case is if the door is opened and then closed again, I have to acknowledge the fact that I've closed the door again before the Q will go high. So there's a couple extra features built into the block that may be useful to you that are different than using an e-stop block for it. In a similar way, the function for two-hand enable is a combination of two 1 out of 1 single channel inputs, IN1 and IN2 shown here. This block does the anti-tie down timing within this discrepancy time, and it also has an enable signal in there to enable the whole operation. I see it down at the bottom. It's, in a simple application, I would use output of this block as an input to a block to say, in this case, I'm just turning on a contactor in enable mode. Again, there's a functional example down here that goes in these in a little more detail and does a couple more things with them, shows some connection to some other devices that may be of interest to you. The muting block for the 1200 and the 1500 is a big block that will allow you to do parallel and directional muting. If you want to do directional muting, again, I'd refer you to the functional example shown at the top of the screen. There's lots of ways to do lots of things there. In the picture I show here, this is simply I'm using just two muting sensors. You see that the mute 01 and 02 are applied to all four channels of the muting. So it's, in this situation, it would be muting sensors arranged in a crossing pattern. But it has built into the block situations where I can clear jammed part in there through the use of the stop input, which is actually the conveyor is faulted, or say I need to clear a jam. So I could put that in, say, manual mode could be the stop input, and then through manipulating the acknowledgement button, I could actually move the conveyor and move the product out of the jammed up area. This one will take a little bit longer to explain, but what we're showing here is that when you have to be aware of some safety considerations if you're using an HMI to trigger some fail-safe functions. The reference at the top here is to a longer functional example that shows a couple of different things that are done in the connection between an HMI and a fail-safe PLC. But right here, what we'll explain will be a simple acknowledgement request done with an HMI. If you look at the logic we show there, that might be a rung out of our reintegration function, where if I were to get an acknowledgement request from, in this case, one of my four fail-safe modules, I would turn on a light just to tell me to push the acknowledgement button. In this case, we're going to send a bit, the ACK REQ bit, we're going to send that to the HMI. In the HMI, and what I'm showing here is a template I use, is I've added two buttons to my template. The yellow button, which is my acknowledge the fault button, and the blue button, which I'm going to use to confirm it. So with those two buttons, what happens is when I get an ACK REQ, I'm going to enable the yellow button. And I'm going to tie those buttons to two safety functions, one of which we've probably seen before, the ACK-GL, which is what it does is it sends a reintegration to all the hardware modules in the project all at one time. The new function that's down in another section of the task chart is the ACK_OP function. And what it does is, if we look up here in network 2, when I press the yellow button, I'm going to send the number 6 to the input of the ACK-OP function block. When that block sees a 6, what it does is it sets the Q output high, in this case the ACK confirm, and it sets a timer. And the timer runs for no more than a minute. And that's as long as the Q output will stay high. So when that ACK confirm goes high, I'm going to use that to enable the blue push button. Pushing the blue push button will send, in this case, a 9. You see the value at the ACK ID input. Yeah, I can change that to different numbers to do different things, but in this case, I'm going to send it a 9. So as long as this function block, the ACK OP, sees the 6, and then it sees a 9 within the minute of time, it'll set the output, in this case the ACK OP, high for 1 scan. And what you'll see down here is now I'll reintegrate all my stuff. Another way to look at that might make a little more sense is through these two screens here. Normally, neither of those buttons is visible. If I get an ACK request, the yellow button becomes visible. When I push the yellow button, it sends a 6, and it sends it for 1 scan, and it sets that timer that only runs for a minute. The ACK confirm is high. That enables the blue push button. I push the blue button, that sends the 9 in this case, and that executes the acknowledgement function. Once the acknowledgement is successful, both those buttons will become disabled again. I was asked this at one of the safety seminars I did about failsafe communication between failsafe PLCs. There are a number of ways to do it, and some of those ways are described in that functional example number shown at the bottom of the screen. But what we'll talk about here is to combine a I/O controller and what's called an iDevice to safely exchange information between two failsafe PLCs. And the reason why this one is easy to use is because there's no additional hardware. There's no couplers or PN to PN modules required to make this happen. If we look at the right side of the screen, we can imagine our project that has two failsafe PLCs in it. In this case, the one at the top is called Demo. The lower one is called Tray. Each of those PLCs also has its own remote rack. The top one is called the I/O device number 1. The lower one is called the ET200SP. And you see from the blue text here which PLC they're connected to. This one to the Demo, this one to the Tray. We see an extra connection, which is the Demo PC has a connection to the Tray PLC. What this means is that the Tray PLC in our project is defined as an I/O controller, and the Demo PLC is defined as an iDevice. It's not difficult to set up. Again, you'll see a little bit of that in the functional example, and I have some other slides that will show in a little more detail. But essentially what you're doing is we're configuring some of the characteristics of, in this case, the Demo PLC, and we assign it to another I/O controller. Forgive me, the names are changed. I have equipment out here where I get the names that are different than I mix my slides up. And we're gonna create a couple of transfer areas to send information back and forth, some failsafe connections. And how they're used is we're going to use a couple of commands that are down in the communication section of the task card, the send DP and the receive DP. So what I'm showing here is that in each of these two PLCs, the first failsafe function in the main safety block is going to be a receive DP, and the last instruction in the failsafe program is going to be a send DP. So what these two blocks allow us to do is to send 16 bits and 2 words in a failsafe manner between the two PLCs. So we see if we follow the green arrow here, the Demo PLC is sending a bit at 0 to a receive bit in the tray PLC also at 0. And we assign that and use those in our programs as appropriate. How they're arranged is they are mated by their DP IDs match. That's how a 2 goes to a 2. And these ladder devices are created when we make those fail-safe connections. On the receive block, these would be the 16 bits I'd use in normal functioning manner. These bits over here represent if any of the sent bits are actually transmitting their safe state. They faulted. They would come across on these other inputs here. But once you get these bits and or words in your program, you're going to use them as you would any other fail-safe I/O. Lastly, I want to talk a little bit about some of the performance level we spoke of in some of the earlier seminars. This simple arrangement here are just some AutoCAD sketches showing a Failsafe 1200 CPU with a Failsafe input module and a Failsafe relay output module. And the point here that I'm trying to make is that the input module shows a single channel Failsafe input internally connected to the input. That single connection and the operation of the terminals on the input module allow that channel to be monitored consistently. And this arrangement, just doing the math from the performance level requirements, can qualify as a PLD circuit. However, if we look, because it's only a single channel on the input, the category of this entire circuit is at best a category 2 circuit. It's only a single channel on the input. So if we look at our performance level chart from here, is that in a category 2 arrangement, I could only use this really if I had identified my risks as being of a medium value. High risks, I would have to make everything in there dual channel. I mention this because hopefully more of you are examining the PLD requirements and using some of those softwares that allow you to measure the performance levels or the SIL of your circuits. You can get them mathematically, but there are some certain restrictions that you have to consider that may not make that simpler hardware solution the right solution. That's all I have for today. So I want to thank you guys for listening so long. And as Jeff mentioned, if you have any questions, you can write them in there, and I'll stay on the line here for a little bit, and we can answer any questions if there are any. Otherwise, thanks for your time, and I will see you next time.
Thank you, Steve. Right now, we don't have any questions in the question box. We'll wait a minute or so and see if anybody types anything in. Also, those of you who are out there, if you are challenged with trying to do safety designs, speak to your C&E salesperson, and they can pull Steve in to help you with that, as well as Heinz Knackstead, who is another safety specialist here at C&E. So these guys do all day, every day. They work with safety products and understand the safety standards and can help you with that process.